Welcome to the Deep Dive. This is where we take a stack of sources, dig through them, and pull out the key insights just for you. Today, we're tackling, well, the ultimate origin story. Really the birth of our own planet, Earth.
That's right. We're going back, way back.
Imagine a time over 4 billion years ago. It's a period so ancient, so mysterious, we call it the Hadean.
Hadean, like Hades.
Yeah.
Implying, hellish conditions.
Exactly. This is roughly 4.5 down to 4 billion years ago. Think chaotic, fiery infancy, before stable continents, maybe even before a truly solid crust like we know it.
And finding direct evidence, it's incredibly difficult.
It really is. It's like, I don't know, trying to find one specific grain of sand on this huge beach that's been battered by storms for, well, billions of years.
Yeah, that's a good way to put it. What's fascinating, or maybe frustrating for a geologist, is that the Hadean eon, it's so significant, but it remains pretty enigmatic, almost a phantom era.
Phantom era, I like that.
Because most of that early geological record, it's just gone. Eroded away or heavily altered by everything that happened since.
So our deep dive today is essentially a geological detective story.
Absolutely. We're looking at a scientific paper that's trying to unlock secrets about Earth's very first crust. And they're doing it by examining some of the oldest rocks ever found.
Right. And the star witness, you could say, the potential smoking gun in this ancient mystery, is the Nuvvuagittuq Greenstone Belt, the NGB.
Up in northeastern Canada.
Yeah. Its status as potentially the oldest bit of crust on Earth has been really hotly debated.
Which is why pinning down its age is just so critical. It's this incredibly rare window, maybe our only window, into Earth's earliest days.
Okay, so studying this earliest crust is hard. Why exactly? What are the main challenges?
Well, like we said, the main thing is just how sparse those early records are. Imagine trying to piece together a giant jigsaw puzzle, but 99% of the pieces are missing or totally warped.
Right.
Most ancient rocks have just been worn away, or they've gone through such intense geological processes, heat, pressure, that their original features are basically lost.
Okay, so when we talk about the oldest rocks we do have, what are we usually referring to? What are the sort of geological benchmarks?
Good question. Usually, when we talk about oldest markers, people think of the Acasta Gneiss complex. That's also in Canada.
Right.
It clocks in around 4.03 billion years ago.
Hmm.
That's generally seen as the boundary marker between the Hadean and the next eon, the Archean.
Okay.
And then you have these tiny, incredibly tough minerals called zircons. They can be found as detrital grains, meaning eroded out of older rocks, or as xenocrysts, trapped in younger rocks.
Like little time capsules.
Yeah, exactly. They're the only undisputed direct samples from the Hadean. But here's the catch.
There's always a catch.
The host rocks they originally formed in, they're gone. We find these zircons loose, or embedded in much younger rocks. So they tell us a piece of Earth existed way back then, but not about the actual ancient crust they came from.
It's like an ancient message in a bottle, but the bottle smashed long ago.
Precisely. You've got the message, but not the context.
Okay, so if zircons, these tough little guys, don't quite tell us about the first crust itself, why focus on mafic rocks? What's special about them?
Yeah, that's a really critical distinction. Zircon-bearing rocks are usually felsic. Think lighter-colored rocks like granite. They often form when older crust gets remelted.
So they're second generation, in a way.
Often, yes. They don't typically represent that very first stage of crust forming directly from the mantle. Mafic rocks, though, like basalt, the dark, heavy rock that makes up today's ocean floor, they are derived more directly from the Earth's mantle. So they could represent that initial crust, the planet's first skin, the big challenge. They usually lack zircon, which is our best dating tool.
Right, the zircon problem again.
And they've often been heavily metamorphosed, cooked and squeezed, which messes up the original age signatures from other dating methods. Still, because mafic rocks might have been a huge part of Earth's earliest crust, figuring out their age is absolutely vital.
Which brings us right back to the Nuvvuagittuq Greenstone Belt, the NGB.
Exactly. This place is dominated by a specific unit called Ujaraluk. It's made of altered volcanic rocks specifically, these things called cummingtonite-rich metabasalts.
Fancy name.
Hey, yeah. But scientists basically interpret this as a remnant, a vestige of ancient oceanic crust.
So exactly the kind of mantle-derived rock we need to understand that first crust.
Precisely. And for, well, over a decade now, the NGB has been smack bang in the middle of this huge scientific debate about its actual age.
How big a debate? What kind of ages are we talking about?
The estimates have ranged from maybe only 3.75 billion years old?
Still incredibly old.
Oh, absolutely.
Yeah.
But ranging all the way up to a staggering 4.3 billion years old.
Wow, that's a massive difference. 500 million years. That pushes it deep into the Hadean.
It does, and that's a huge deal when you're trying to understand the planet's first few 100 million years.
So what was the initial evidence pointing towards that really ancient 4.3 billion year date? What got scientists excited?
Okay, so the initial buzz came from studying isotopes, specifically isotopes of an element called neodymium-142 to be exact.
Right.
N142 is produced by the decay of samarium-146. Now, SM-146 has a very short half-life, geologically speaking, decays quickly and was essentially extinct, gone by about 4 billion years ago.
So any variations in N142 must have happened before that 4 billion year mark.
Exactly. It's a signature only the very earliest Earth processes could create. And when researchers plotted the N142 data from the Ujjarlik unit, it formed a correlation what geologists call an isochron that seemed consistent with an age of around 4.3 billion years.
Okay, so that sounds promising. But then you said this Hadean age got challenged. Why? What was the counterargument?
Well, the challenge came down to interpretation. Some scientists argue that the pattern seen in the N142 data wasn't actually an isochron showing the formation age. What else could it be? They proposed it was a mixing line. Imagine you have your original rock and then later maybe fluids or melts with a different enriched Hadean signature mixed with it. That mixing could mimic an age pattern, but it wouldn't be the true age of the rock's formation.
Ah, like geological contamination messing up the signal?
Sort of, yes. Plus, when they tried to date zircons found within the Ujjarlik unit using the standard uranium-lead method,
The reliable zircons again.
they consistently got much younger ages, Neo-Hadean ages around 2.5 to 2.8 billion years old.
That's way off from 4.3 billion.
Way off. The interpretation was that these younger ages weren't the original formation age, but the age of a later metamorphic event, a time when the rocks were intensely heated and squeezed, resetting the zircon clocks.
So the zircons recorded the cooking, not the baking.
Nicely put. And even other dating systems, using long-lived isotopes like samarium-147 decaying to neodymium-143 or lutetium-176 to hafnium-176, also showed signs of being disturbed after the rocks originally formed. It made getting a clear original crystallization age really tricky.
Okay, so if these NGB mafic rocks weren't Hadean, what was the alternative age people were suggesting?
If they weren't Hadean, the most likely alternative age was around 3.77 billion years,
Why that specific age?
because that's the age of associated felsic rocks. Those lighter, potentially later-stage crustal rocks found within the same NGB belt. So maybe the mafic rocks were just part of that same slightly younger Eoarchean event, still ancient, but definitely not Hadean.
It really sounds like the usual go-to, the zircons, were kind of sending them down the wrong path, or at least a confusing one.
They were recording an age, just not the one everyone was hoping for the original igneous age.
So if the zircons weren't cooperating, what was the new approach in this paper we're looking at? What was their clever workaround?
This is where the new paper gets really interesting. They shifted their focus quite significantly. Instead of looking primarily at the main Ujjarlik unit itself.
The metabasalts, right.
Right. They turned their attention to these distinct maclevic intrusions. These are basically sheets or bodies of magma that pushed their way into the existing Ujjarlik rocks and then solidified. Specifically, they looked at metagabbros.
Gabbro being a coarser-grained version of basalt, essentially.
Yeah, similar mafic composition, cooled a bit slower underground. And the key insight here is, if these metagabbros intrude the Ujjarlik unit, they must be younger than it.
Ah, okay. So dating the intrusion gives you a minimum age for the rock it cuts into.
Exactly. It's a fundamental geological principle called cross-cutting relationships. If feature A cuts feature B, feature A is younger. So the age of these intrusions puts a floor under the age of the Ujjarlik.
Clever. And you mentioned there were different types or generations of these metagabbros.
Yes, that's important too. There are younger, coarse-grained Neoarchean metagabbros in the area, which had already been reliably dated using zircons to about 2.69 billion years old.
Okay, so ignore those.
Right. This study focused specifically on an older generation of metagabbros. These ones are different. They have a finer-grained, layered, or gneissic texture, and they can be traced as distinct bodies, like sills, running for over a kilometer within the Ujjarlik unit.
And what made these older intrusions particularly promising for dating, besides the cross-cutting thing?
The crucial feature was that they show clear signs of magmatic differentiation as they cooled. Meaning, as the original magma cooled and solidified, Different minerals crystallized and settled out at different rates. This created distinct layers within the intrusion, some layers richer in, say, plagioclase feldspar, others richer in hornblende. You see these gradual changes in mineral proportions.
Okay, so the intrusion isn't just one uniform block of rock. It has internal variations from its cooling process.
Exactly. And that internal variation, that chemical fractionation, turns out to be really important for the dating method they used.
So did the zircons in these differentiated metagabbros finally cooperate? Did they give the Hadean age?
You'd hope so, wouldn't you? But, no. Still no luck with the zircons.
Oh, come on.
Even in these older, differentiated metagabbros, the zircons they managed to find and analyze gave Neo-Archean UP ages, mostly around 2.64 to 2.66 billion years, maybe one at 2.76 billion.
So the same metamorphic overprint again?
Looks like it. The zircons had features like rounded shapes, low ratios of thorium to uranium, suggesting they've been recrystallized or strongly affected by that later metamorphic event, not preserving their original igneous age. Zircons were just not the key here.
Okay, I'm on the edge of my seat. If not zircons, what was the breakthrough? How did they finally crack this ancient code?
The breakthrough came from going back to the samarium-neodymium system, the SM-end isotopes.
Ah, the system that gave the original hint of a Hadean age but was then questioned.
Exactly. But this time, applied differently. They focused on these differentiated metagabbro samples where the magnetic process had created that internal variation we talked about. And crucially, the SM system seemed less disturbed by the later metamorphism in these specific rocks compared to, say, the lutetium-hafnium system.
Okay, so SMN seemed more robust here.
It did. And this is where it gets really compelling because they didn't just use one SMN clock, they used two.
Two clocks? How does that work?
They analyzed isotopes related to both the long-lived SM-147 decaying to N-143 system, that's the standard one, with a half-life of over 100 billion years.
Okay, the slow ticker.
And the short-lived SM-146 decaying to N-142 system. Remember, SM-146 was extinct by 4 billion years ago.
Right, the one that gave the original controversial Hadean hint in the Ujaralik rocks.
Precisely. They analyzed both systems in multiple samples taken from within the same differentiated metagabbro intrusion, samples linked by that igneous fractionation process.
And what did they find? This is the moment, right?
This is the moment. The crucial result was that both systems yielded remarkably consistent Hadean ages.
Both of them at the same time.
Yes. For the samples from this study, the long-lived system gave an age of about 157 million years, plus or minus 174 million. The short-lived system gave 496 million years, plus 53 minus 81 million.
Wow. Those ages overlap perfectly within their uncertainties.
They do. And when they combined this new data with previous SM data from other NGB metagabbros believed to be part of the same suite, the consistency held up. Around 431.19 plus 401.58 Ma for the long-lived, and 401.76 plus 54.87 MAVR for the short-lived. Essentially around 4.1 to 4.2 billion years ago.
Okay, that consistency across both systems in rocks that clearly form from the same cooling magma, that feels different. That sounds really solid.
It is. It's incredibly compelling evidence. This is the aha moment.
Why is the agreement between the two so important? Why does that rule out the mixing line idea?
Because the short-lived SM-146 system was extinct by 4J. Any later mixing event, say during that Neochean metamorphism around 2.7 Ga, could not create a false age signal in the 147 system that also perfectly matched the age signal from the completely independent, long-lived 147 SM and 143 N system in the same fractionated samples.
Ah, okay. The mixing couldn't fake both clocks to show the same ancient time.
Exactly. For both clocks to align like this across samples related by igneous processes, the age has to be real. It strongly argues against the mixing hypothesis and points to a genuine Hadean formation event. The possibility that you had two separate, unpreserved Hadean reservoirs coincidentally creating these signatures in different rock units is also just extremely unlikely.
So the geological detective story has a verdict.
I think it does. The verdict from this evidence is that these metagabbro sills, these intrusions, really did form and magmatically differentiate way back in the Hadean eon. Around 4.16 billion years ago seems like a solid number based on this.
That's profound. Okay, so let's unpack the implications. Since these 4.16 billion-year-old metagabbros cut through the Ujaralik unit,
it sets a minimum age for the Ujaralik unit itself.
Meaning the Ujaralik metabasalts, that potential ancient oceanic crust, must be at least 4.16 billion years old.
Correct. It firmly places the Ujaralik unit, therefore potentially some of the earliest oceanic-like crust on Earth, squarely into the Hadean.
That is a huge confirmation. It provides this almost unbelievable window into Earth's earliest times.
It really does.
And what do the isotopes in these ancient metagabbros tell us about the Earth's mantle back then? The source they came from?
Well, looking at the initial neodymium isotope ratios, specifically something called initial epsilon 143 end-end and mu 142 end, they found values close to zero or slightly positive, like plus zero point 0.5 and plus zero point 0.9 respectively.
What does that mean in plain English?
It suggests these Hadean mafic rocks came from a mantle source that was pretty close to chondritic.
Chondritic-like, chondrite meteorites, the primitive building blocks.
Exactly. It implies that the early Earth's mantle, at least the part sourcing these magmas, hadn't yet undergone massive chemical differentiation or developed really extreme, exotic chemical reservoirs, which some models had proposed.
So the early mantle was maybe simpler, more uniform than we thought?
Or at least this part of it was surprisingly close to the expected bulk composition of the early Earth, derived from those primitive meteorite ingredients. It kind of argues against needing really weird, super-enriched, hidden reservoirs deep in the Hadean mantle to explain these rocks.
Okay, so stepping back from the specific rocks, what's the bigger picture here? The wider relevance of finally pinning down this Hadean age for crustal rocks.
Well, connecting it all, this discovery gives us invaluable concrete data points for the Hadean Earth. It strongly supports newer geological models that suggest Earth might have actually had quite extensive mafic crust during this very early period. Maybe not stable continents like today, but a widespread basaltic skin.
Right.
And it opens the door to tackling some really fundamental questions about our planet's origin story.
Like what?
Like, how did the very first crust actually form? What did plate tectonics or whatever passed for tectonics back then look like? What was the chemistry of the oceans interacting with this crust? And, maybe the biggest question of all, what were the environments like where life might have first emerged?
Finding actual Hadean crust gives us a tangible piece of that environment to study.
Precisely. It helps us piece together the literal ground floor, the blueprints of our home planet.
Wow. This deep dive has really been a journey back billions of years. It's amazing to think we can scientifically peek into Earth's formation like this.
It's a testament to decades of work,
Yeah.
improving analytical techniques, and sheer persistence in tackling these incredibly challenging rocks.
Absolutely. But even with this incredible discovery, finding this 4.16 billion-year-old marker, the Hadean eon still feels largely mysterious, doesn't it?
Oh, absolutely. We've opened a really important new window, but there's still so much we don't know about that truly alien early Earth. This is likely just one piece of a much larger, more complex puzzle.
It makes you wonder, if these mafic intrusions are indeed a preserved piece of Earth's original skin, what other incredible secrets are still locked away out there, hidden in the oldest rocks on our planet, just waiting for scientists to find the key?
That's the exciting part. There could be more NGBs out there, or other Hadean fragments yet to be discovered or fully understood.
And what could really understanding Earth's beginnings, this fundamental origin story, tell us about, say, the potential for life elsewhere in the universe, or even maybe projecting forward about the long-term fate of our own world?
Those are the grand questions, aren't they? Understanding how our habitable planet formed is surely step one in understanding how other habitable planets might form, or what makes Earth special. It's foundational science.
A truly foundational deep dive today. Thanks for walking us through it.
My pleasure. It's fascinating stuff.